One of our tasks in Chapter 6 is to compute Riemann sums, and you can see here in problem 10 we're asked to do just that. We're asked to compute the Riemann sum for this function, f of x equals x cubed, over the interval 0, 1. We're going to choose some representative points using midpoints of the subintervals. And I'm going to focus on letter B here. So I'm going to work on using 5 subintervals of equal length. Let's start by reviewing the steps that we need to compute these Riemann sums. So basically we're going to graph the function over the interval. Sketch it's fine. We're going to calculate the subinterval. We're using equal width. And so the way we do that is we call this width delta x, and we do b minus a over n, where b is the right-hand endpoint of the interval, a is the left-hand endpoint, and then n is the number of subintervals. We're going to make a list of the subintervals. We're going to choose our representative values. In this case, we're using midpoint, right? We'll figure out the function values for each of those representative values. And then we'll go ahead and we'll compute the Riemann sum, which is an area approximation. And then again, make sure you're answering the question posed. In our case, we're just supposed to compute the Riemann sum. So let's just start with a quick graph of y equals f of x, which is x cubed. So this function here is x cubed. And I've just graphed it on the interval 0, 1. So 0, 1 starts here at 0 and goes all the way over here. So we're basically concerned with the function between 0 and 1, and this Riemann sum that we're computing is going to approximate this area underneath the curve between the x-axis and the blue curve. So that's kind of our goal in a graphic sense. You really don't even need the graph to compute the Riemann sum once you get the hang of it, but I'm just showing here what it is that we're trying to get. Okay, let's get organized. So let's just start by getting organized. We know that we're working with the function y equals x cubed. We know we are on the interval 0, 1. And so this tells us that a, in our case, is 0 and b is 1. And we use those along with the number of subintervals, which we've set as 5 because we're working on 10b. We use those to find the subinterval width, which we call delta x. And that subinterval width for us is 1 minus 0 over 5, which is 1/5. And it might actually be better to write that as a decimal, 0.2. And then what we're going to do is we're going to use this subinterval width to make 5 subintervals. Let's go back to that graph and see if I can show you what this means. So here's our picture, and remember that we're working between 0 and 1, so our boundaries are like here and here. And then what we want to do is divide this interval 0, 1 into 5 subintervals. And we know that the subinterval width is 0.2. So basically our first subinterval is going to be from 0 to 0.2. Our next subinterval is from 0.2 to 0.4. The third one is 0.4 to 0.6. The fourth one is 0.6 to 0.8. And then the fifth one is 0.8 to 1.0. And what we're going to do for each of these subintervals is we're going to mathematically find the area of a rectangle. So the way we'll do that is in any particular subinterval, we'll go ahead and we'll draw a rectangle. And remember that we've decided to use the midpoints of these intervals as our representative values. So the midpoint between 0 and 0.2 is 0.1. The midpoint between 0.2 and 0.4 is 0.3. The midpoint between 0.4 and 0.6 is 0.5, and so on. So these are our midpoints. And those representative values, those are the values that we use to find the heights of our rectangles. So if I plug 0.9 into the function, follow that up here, I get a function value which gives me a height, and then I make my rectangle over that particular subinterval. Same thing with 0.7, you'll see that that y value is about right there, and so I'll make that rectangle. And we can do that for each of these subintervals, 0.5, 0.3, and then of course 0.1 is barely visible, but there is a little rectangle there. All right. And the idea is that if we find the area of these rectangles, which is very easy to do, just length times width, or in this case width times height, we can approximate that blue area that we talked about earlier. It's going to be an approximation. It's close. It's not perfect. You can see we missed some spots here. We missed all these spots, and we also went over in certain spots right here with these corners. So it's not a perfect approximation, but that's our goal. So let's get back to those calculations. Our subintervals, remember, were from 0 to 0.2, from 0.2 to 0.4, from 0.4 to 0.6, 0.6 to 0.8, and from 0.8 to 1. So those are our subintervals, and from there we chose representative values, the midpoints. Our midpoints were 0.1, 0.3, 0.5, 0.7, and 0.9. Depending on what type of Riemann sum you're computing, you may not use the midpoints. You might use the left-hand endpoint or the right-hand endpoint. So be sure to choose the correct representative values for the problem that you're solving. Okay, we've got our midpoints, and now we need function values. So we need f values for each of these representative x values. And what that means is I have to cube these. So I've gone ahead and done that already. When you cube 0.1, you get 0.001. And when you cube 0.3, you get 0.027. 0.5 cubed is 0.125. 0.7 cubed is 0.343. And then 0.9 cubed is 0.729. Now these are our function values, and in terms of our graph, these represent the heights of each of our rectangles. These are the f values associated with those midpoints. So if we want to compute a Riemann sum, we're going to take each of these f values and multiply them by our width, which was 0.2. So our sum, which I'll just call capital R, our sum is going to be the product of 0.2, which is the width, times the sum of all the heights. So 0.001 plus 0.027 plus 0.125. You get the picture. Let me write this as a product with parentheses instead of the curly bracket here. So this is an actual expression here, 0.2 times this sum. Well, I typed it all in, and when I did that, my value for my Riemann sum came out to 0.245. And not only is this the value of the Riemann sum, but it's also an approximation for that area underneath the curve. And we're going to find out later that we can find the actual value, and it turns out that that's 0.25 or 1/4. So this is a pretty good approximation. So this is the process for finding Riemann sums. Just quickly, let me summarize what we did. We divided our interval up into subintervals, in this case 5 subintervals. We found our representative points, in this case midpoints. we plugged those represented points into our function x cubed, and we came up with these y values, which are heights. And then we computed our Riemann sum, which is our delta x times the sum of our function values. And when we did that, we came up with an answer, a value of 0.245. Good luck with your work.